Hi everyone. So today's lecture is we're gonna start chapter 10, which is about statistical inference and hypothesis testing. And before we actually get into hypothesis testing, the first thing that I want to discuss are confidence intervals, since they're really another important tool and another important component of statistical inference. And usually, most of the time, whenever we're talking about statistical inference, we start out by introducing confidence intervals first. So what are confidence intervals? So confidence intervals are essentially intervals that provide information about plausible parameter values. So they're statements about parameters, and they're of the form that looks like this. And there's a slight typo. Let me just write L parentheses U. So L is the lower endpoint of the confidence interval. U is the upper endpoint of the confidence interval. And it turns out that there's a close connection between confidence intervals and hypothesis tests. So if a confidence interval is based on the same statistical method as the hypothesis test, then you can reach the same conclusions with the confidence interval. And in fact, a lot of journals are requiring researchers to report not just p-values from a hypothesis test, but confidence intervals, so that you can get an idea of plausible parameter values. Okay, so what's the general idea? The general idea is that a confidence interval captures the true parameter value 100 times 1 minus alpha % of the time. And I'm going to discuss further what this alpha is, and you're going to see it when we go into hypothesis tests too. So if the null value, typically the null value is 0 when you're looking at comparing means, or 1 if you're comparing ratios, for instance risk ratio or odds ratio. If that is outside of the confidence interval, then you have a significant result. So what that means is essentially 0 is, or the null value, is not a plausible value for your parameter. If on the other hand, if it's in the confidence interval, so if the null value is in the confidence interval, then that would mean the null value is a plausible value, so you would not reach significance at level alpha. So we're going to discuss this in more detail later on, these terms alpha and this confidence level that I've written here. But let's talk about variability. So knowing the variability of our sample statistics are essentially not just the variability, but also the distribution of the sample statistics allow us to construct these confidence intervals. So some general properties of confidence intervals. Your confidence interval width is going to increase if you increase your confidence level. Okay, so for instance, a 99% confidence interval will necessarily be wider than a 95% confidence interval, because you have to have more confidence for a 99% confidence interval, so you must include more values to obtain or to achieve that additional level of confidence. Okay, one important point to point out is this bullet here. The interpretation of confidence intervals is a little bit subtle. And what I mean by that is, for instance, we won't say things like there's a 95% probability that mu is contained in the confidence interval that we computed. So we would actually want to scratch this out and not say a statement like that. So the question is why? Okay, and the reason why is because let's just say we computed a confidence interval. This is just a hypothetical one for a mean mu. We're interested in a population, some population mean mu, and we've computed a confidence interval for this guy. Let's say it's a 95% confidence interval from sample data, and we found that this 95% confidence interval was from 4.5 to 7.5. So this is our 95% confidence interval. And the reason that we can't say things like there's a 95% probability that our mu is in here is because mu is either in there or not. Okay, so mu, remember, a population parameter is a fixed unknown constant. So it's a fixed unknown quantity, and it's either inside this interval or it's not inside that interval. And that actually happens with probability 1. So the population mean is either contained in this interval or not. So the interpretation for confidence intervals, let's take this away, is a little bit subtle. And what we can say, or how we actually do say this, is we say that we're 95% confident that mu is contained in the confidence interval. We don't say that there's a 95% probability that mu is contained in this confidence interval. This is just one of the quirks of frequentist statistics, and that's just how it works out. Okay, so we introduced earlier this term alpha, and you're going to see it even more when we discuss hypothesis testing. And alpha is essentially our significance level, and for most of the medical research, it's set at this default level of 0.05. I know this is somewhat arbitrary, and this exact value, from what I understand, is due to R.A. Fisher and his thinking that 1 out of 20 is a relatively rare event. Okay, so if we've got this level of significance, alpha equals 0.05, then sometimes we'll also talk about the confidence level, or level of confidence, and that would essentially just be 1 minus this alpha. So if our level of significance is alpha, then I'll write up here confidence level would then be (100) times 1 minus alpha %. So if we were dealing with a 0.05 significance level, or if we were dealing with an alpha of 0.05, that would translate to a 95% level of confidence. Okay, so since we've made the point on this previous slide, and I'll just go back this point, that we can't say things like there's a 95% chance or 95% probability that mu's in the confidence interval that we compute, then how should we interpret? So what exactly does the confidence interval mean? Well, basically what it means is that if we have, say, a 95% confidence interval, and we were able to repeat our experiment 100 times, so we would collect data, same sample size, everything, compute, say, the mean in all of these 100 data sets, and compute the confidence interval in all of these 100 for all of these 100 data sets, then 95 of them would contain the true value. So if we were talking about the mean, then 95 of those 100 confidence intervals for that we compute from these samples would contain the true population mean. Okay, so the confidence interval interpretation is about what would happen if we did repeated sampling, if we repeated our experiment over and over. And again, once the confidence interval is computed, it either does or does not contain the true value. Okay, so how do these things look? So for normally distributed statistics, the 95% confidence interval looks like this. So if your sample statistic that you compute for the data, and we're going to see that, for instance, proportions, we're going to appeal to the central limit theorem and look at proportions, which are essentially sample means, but those things are approximately normally distributed. So confidence interval, a walled confidence interval for a sample proportion would look like the sample value, which would be the proportion, plus or minus some number times the standard error of this sample statistic. So where do these numbers come from and what are they? So 1.96 comes from a particular quantile on the normal distribution that's associated with a particular area to the right hand side of that value. Okay, the standard error, so I'll write a normal quantile. This comes from a normal quantile. And this standard error is essentially the standard deviation of the sampling distribution of this statistic. Okay, so it gives you an idea of the amount of variability in your statistic. Alright, what if you wanted a 99% confidence interval? Well, naturally, like we've written on the previous slide, you should anticipate that the interval is going to be wider. So how does that come about? Well, we just pick a different quantile from the normal distribution. So we essentially have to go further out in the tail of the normal distribution and grab a number that's larger, so 2.58 instead of this 1.96 up here. So that's the change that's happened when we increase our confidence level. And the reason we have to do that is because if we want this to attain this additional level of confidence, well, we have to think about more values. We have to include more values. Okay. So one of the most popular distributions in applied statistics is this so-called t-distribution. And if we're talking about means and we're talking about data that comes from a normal distribution, it's actually this t-distribution that we use to form confidence intervals for means and to do hypothesis tests. Okay, so let me erase this. Let's do away with this for now. So I had the t-distribution underlined, and so how does that change the calculation of this confidence interval? Okay, so we're no longer necessarily assuming that our sample statistic comes from a normal or approximately normal distribution. We're assuming that it's distributed as a t. And this is actually valid if your underlying population is normally distributed. If your underlying population is normally distributed, then the test statistic that you compute from the data has a t-distribution. Okay, so what does that do? Well, that just changes these values. So no longer would we be looking at quantiles for a normal distribution. We would be looking at quantiles from the t-distribution, and we would pick the appropriate quantile that corresponds to what confidence level that we want. Okay, so let's look at a quick example and see how this works out. So we're going to assume that we collected data on vitamin D levels from a population that's normally distributed. So we're assuming that this population is normally distributed. Okay, after computing the data and running some numbers, we wound up with a sample mean of 50 nanomoles per liter with standard deviation of 5 nanomoles per liter. Notice that these are in the same units. Okay, and our sample size was n of 25. So n equals 25. So how would we compute, say, a 95% confidence interval for the mean vitamin D levels in this population? Well, naturally we would use our sample estimate plus or minus some notion of how much variation there is in this sample estimate. Okay, so let's take some of this away. So where do these numbers come from? Well, this guy right here, since we've assumed that our underlying population is normally distributed, then we know we can appeal to the t-distribution, and that's precisely what this 2.06 number is. It corresponds to the appropriate quantile from a t-distribution with 24 degrees of freedom because the appropriate degrees of freedom is n minus 1 if we're talking about a one sample situation. And if we're talking about a 95% confidence interval, then what that necessarily means is that our alpha must have been 0.05. So if we look at the appropriate quantile, we should be picking up the quantile associated with a t-distribution with 24 degrees of freedom and area to the right of 0.975. Okay, 0.975. So what does that look like graphically? Well, let's just real quickly draw t-distribution. This is our hypothetical t-distribution. It should have heavier tails than the normal distribution. So I'm going to call this a t-distribution with 24 degrees of freedom. And where does this guy right here sit? Well, that value would sit somewhere out here, so that would be your t quantile, 24 degrees of freedom, 0.975. So what does that mean? Well, that means that 0.975 of the area underneath this curve, remember this is a distribution, it's a t-distribution, so it has a area of 1 or 100% under the curve. So what does that mean? So it means that this particular quantity, t 24 degrees of freedom and 0.975, corresponds to this point such that all the area to the left of this is equal to 0.975. So since probabilities should add to 1 for complementary events, it means the area to the right of this should be 0.025. So I'll just write that area is 0.025. And if I drew the corresponding negative value of this number, so let's just pretend that's here. So we've got negative t 24 0.975. So since the t-distribution is symmetric about 0, that would also mean that the area to this, on this side, of the negative of this number is also equal to 0.025. Okay, so if the area in the tails, so out here is 0.025, out here is 0.025, and since this guy's obviously a distribution, it means the area inside here should be 95%. So this is why we have chosen the quantile in this way, with 24 degrees of freedom and this area to the left of 0.975. Because if we do that, if we choose the quantile in this way, then the amount of area between this quantile and its negative is 95%. Okay? So that's why the appropriate quantile takes this form. Alright? So what we see here from this simple data example is the 95% confidence interval for our population mean vitamin D levels is within this range, and this works out to be a confidence interval with lower endpoint 47.94, nanomoles per liter, and upper endpoint of 52.06 nanomoles per liter. So this would be our 95% confidence interval for mu, where mu is the population mean vitamin D levels. Okay, so confidence intervals are statements about parameters. They are not statements about statistics. Remember the difference from a few lectures ago between statistics and parameters. Parameters are population characteristics, and statistics are things that we compute from the data. Okay? Okay, so an important quantity in forming these confidence intervals is this so-called standard error, and you've seen it. I'll go back a slide. You've seen that here. Okay, so I kind of glossed over that last time, but in this computation for the 95% confidence interval in this situation, we had the t quantile, the appropriate number that we should get from the t distribution. Remember that the t distribution is valid if we're assuming that our population is normally distributed, and there are formal ways to tell if that's true or not. Okay, I shouldn't say to tell if that's true. I should say there are formal ways to determine if there's evidence either for or against that assumption. Okay, and additionally, what you'll see out here is this other number, and that's going to be the standard error for this particular case. Okay, for this particular example. All right. So what is the standard error? The standard error is essentially the standard deviation of your sample statistic or your test statistic. Okay. And the sample error, the standard error for the sample mean, it's closely related to the population standard deviation. Okay. So if you're interested in, say, x bar, then the standard error of x bar has this form. Okay, so this is like the standard deviation of your sample mean. Okay, and you'll notice what happens here in this formula. So what happens if you increase your sample size n? Well, this denominator gets larger, and the overall quantity gets smaller. So as you increase your sample size, you can see from this formula that your standard error in the mean decreases. So if you were able to take an infinite number of samples, then essentially your standard error for your mean would go to 0. Okay? What happens if this guy, this square root of n in the bottom, what happens if this guy decreases? So you decrease your sample size. Well, if you decrease the denominator in a fraction, then the whole quantity will increase. So for smaller sample sizes, the standard error for x bar is larger. Okay. Now, unfortunately, we typically don't know what the population standard deviation is. If we don't even know what the mean is, we're typically interested in doing inference about the mean. So if we don't even know what the mean is, the population mean is, we probably don't know exactly what this population standard deviation is either. So since we don't know that, we have to go through a different route in order to talk about the standard error of x if we want a good estimate of that guy. So since we don't know sigma, we'll typically use an estimate of this. So in this expression, what I have here is standard error hat. So that lets you know that this is the approximate standard error of your sample mean. And all I've done here is replaced sigma with the sample estimate of sigma. So I've replaced the population standard deviation with the sample estimate of that population standard deviation. And of course, as your sample size gets larger, this S gets closer and closer and closer to looking like this sigma. So this standard error won't be an approximation anymore. It would be exact as n becomes very large. Okay? So this is what the standard error for just a regular sample mean looks like, and how you use the data in order to estimate it. What about for the difference in two sample means? Because you can probably already guess that if we're interested in, say, testing the difference between two groups, and we have continuous data, we're probably going to be, this is going to be kind of a foreshadowing, but we're going to be interested in a test like this, right? Where we're trying to see whether or not the mean, say, in a treatment group is equal to, say, the mean in a control group. And you can probably already guess how you, or at least a very first step, how you would go about assessing that. Well, naturally, you'd look at the difference in the two sample means, right? You would take a sample from the treatment population and compute the sample mean, and you would take a sample from the control population and compute the sample mean, and you would try to gauge how different are these sample means. Well, probability is going to allow us to quantify how different and the level of evidence either for or against this. But you can definitely see that this would be your first starting point, is to compute the actual sample means, and maybe the first step would be just to eyeball it and see if it looks like anything's going on. Okay, but if we want a more precise treatment of this, we need to also nail down, well, what's the standard error of the difference? So how much variability should we see in this difference? Okay, so that leads us to the standard error of the difference in the sample mean in the treatment group and the sample mean in the control group. And actually, I should write a hat here, so make sure you correct that. Okay, and the reason I should write a hat here is because I don't have sigmas anymore. I have S's. So these are the sample estimates. If I didn't want to put a hat, I would just rewrite something like this: the standard error of x bar t minus x bar c would be something very similar, but it would look like this: sigma t squared over the number in the treatment group plus sigma c squared divided by the number in the control group. Okay, but the moment that I replace these population parameters, these sigmas, with s's, then this guy needs a hat. Okay. Okay, so this t-distribution is an important distribution, and it was discovered by Gossett under the pseudonym Student, and he was working for the Guinness Brewery Company when he discovered this t-distribution. And it's one of the most commonly used methods to compare two population means. And so essentially what the t-test does is it's going to determine whether the observed difference in means, so x bar in the treatment group minus x bar in the control group, is larger than what we would observe by mere chance. So is this difference likely due to chance or not? If it is, we could observe a difference like this just by chance, then we wouldn't reach a level of significance. We wouldn't say that there's a difference. But if we have a very small probability of observing a large difference like this by chance, that's when we would reject a null. We're going to talk more on this later, okay? So basically, it would be a comparison of the difference in the mean. So the difference in the population mean mu in the treatment group, and the difference and the population mean in the control group. So we would be interested in whether or not, say, this difference is 0 or not. Mu treatment minus mu control equals 0. So this null hypothesis would be a statement basically that the mean in the treatment group is the same as the mean in the control group. Again, I want to stress what I've written here are statements about population parameters, mu treatment and mu control. It doesn't make any sense to write statements like this. So we wouldn't write a statement like this because it's not interesting and it's not true. It'll most likely not be true. But even if it were, it wouldn't be interesting. So whether the difference in sample means is equal to a particular number or not, say 0. What we're interested in are statements about the underlying population, not statements about things that are going on in the sample. We want to use things that are going on in the sample to say things about the population. Okay? So how is this t-distribution used in the two-sample case? Well, if we're willing to assume that both populations, so if both populations are normal and they have equal variance, then the difference in sample means, so that's this numerator, scaled by an appropriate estimate of the standard error, which I'm calling SE sub p, so the pooled estimate of the standard error of this difference, then this quantity follows a student's t-distribution. Okay, so let me take this away. So this pooled estimate of the standard error looks like this, and it's not really important to know the exact definition of these formulas. Really, what you need to know is this pooled estimate S sub p squared is a weighted average of your individual variances here. Okay, and the reason that it's a weighted average is because if you take the weight that's in front of this guy and add that to the weight that's in front of this guy, then you would get 1. Okay, so this pooled estimate would give more weight to, say, the treatment group if there were more individuals in the treatment group versus the control group. So for instance, if NT were much greater than NC. Now, vice versa, it would give more weight to S squared sub C, so the variance estimate in the control group if we had more individuals in the control group versus the treatment group. So for instance, if NC were greater than NT. Okay. And another thing to notice is this denominator here. Alright, so this n sub t plus n sub c minus 2. So number of individuals in the treatment group plus number of individuals in control group minus this 2. So why does it look like that? Well, again, this n sub t plus n sub c minus 2 is the so-called degrees of freedom in the two-sample case. And the reason that we've subtracted 2 is because we're estimating two means here. In the previous example, when we gave the kind of intuitive reason for why we divide by n minus 1 when we're computing the sample variance, it's because we used up 1 degree of freedom when we estimated the sample mean, which was required for the sample variance formula. Okay, same kind of intuition here. We're subtracting 2 from the total right? So n sub t plus n sub c would be the total, the number in treatment group plus the number in control group, and then minus the number of means that we're estimating. Okay, so we're estimating mu control with x bar control, and we're estimating mu treatment with x bar treatment. Okay. And if we want to grab the appropriate t quantile in order to form the confidence interval, or to find out where the rejection region is, we would typically look in a t-table at the appropriate t distribution with the appropriate degrees of freedom in order to find those quantiles or rejection regions. We're going to talk a little bit more about rejection region and p-value in the upcoming lecture. So conclusions for this lecture, this was an introduction to confidence intervals, and confidence intervals are usually one of the most natural starting points when we start talking about inference. And essentially they're intervals that describe plausible values for the particular parameters that we're interested in. In the previous slides we've talked about mean as being the primary focus, but you can form confidence intervals for parameters other than means. Okay? For continuous data, the t-distribution is used to construct confidence intervals and do hypothesis tests to compare means. Okay? Now if your distribution is skewed, or you find out that it looks like the normality assumption could be violated, or you have outliers in your data, then we're going to talk about ways that you can still do comparisons, but you will no longer be using the t-distribution. You would be doing these so-called non-parametric tests. Okay? But for now we're going to focus on using the t-distribution and going with the underlying assumption that our population is normal when we do confidence intervals and hypothesis testing in the next few lectures. Okay, so next time we will discuss hypothesis testing, how you carry it out, what are the kind of mechanisms and need to knows there. Thank you.